I'm Yang, a master's student from Tongji University. It's a pleasure to be here and present our work, event-based driver distraction detection and action recognition. So driver distraction detection is a very important task for road safety. Researchers have tried different approaches, including visual sensor, physiological sensor, or physical sensors. From the perspective of computer vision, the problem can be combined with the action recognition and uniformly formulated as video understanding task. However, despite the rapid growth of the computer vision, conventional camera-based methods are confronting many challenges, including complex in-cabin light condition, limited computing resources causing latency, temporal information redundancy, and privacy issues. For example, single frame and keyframe methods are still the mainstream approaches, which cast off lots of temporal informations in action. The event cameras are novel bio-inspired sensors that respond to the light intensity change asynchronously and have good properties against conventional cameras. They capture the dynamics of the scene, so that naturally suits the action recognition task. In this work, we exploited event cameras for driver distraction detection and action recognition. Here display our architecture. The event streams are first denoised and voxelized in the pre-processing stage to generate a sequence of event voxel grids. Then the voxel grids features are extracted with, using a light-weighted conv-nets and fed into the LSTM for temporal modeling. Finally, driver distraction and action are predicted. Here shows our training pipeline. The neural network is trained in an end-to-end manner on the simulated dataset with intermodal pre-training and fine-tuned on the real event dataset in a transfer learning method. In the pre-processing stage, we first denoise the event stream with a simple temporal spatial neighborhood filtering. Then, since the event streams cannot be directly processed with neural networks, we use event voxel grid representation to encode the event streams into three-dimensional tensors that contain spatial and temporal information simultaneously. To fully exploit the temporal sequential characteristic of event camera, of event data, we apply overlapping sliding window on the temporal dimension to generate a sequence of voxel grids rather than a single voxel grid. In this way, the temporal information is decomposed into multiple steps and can be processed sequentially, which can better encode the strength of semantic change. The bottom right image shows the result where the B and T dimensions are flattened. When partitioning the event streams, previous practice used either a fixed number of events or fixed time duration, resulting in changing time steps that may differ by more than 10 times in length, causing significant computation inefficiency. Our adaptive segmenting method produces fixed numbers of segments of evenly allocated events. This method is computation efficient and adaptive to different scenarios without parameter searching. As for the dataset, since large-scale event datasets are unavailable in the current stage, we use V2E to simulate event dataset from the large-scale multimodal dataset Drive and Act. The dataset contains about 10,000 clips of average duration of 3 seconds, and fine-grained action label of 34 classes. We ensure fair comparison on the dataset for action recognition. And and what's more, we collect a small real dataset with Davis 346 camera by ourselves for validation. The real event dataset contains over 1,500 clips. The experimental results are displayed here. The results show the effectiveness of our method for both tasks. Our method outperforms most RGB-based methods and performs on par with the state-of-the-art method. Representative results show our model recognizing actions without conventional dependency. That is, our model directly recognizes the motion rather than relationship between objects. For instance, as the representative results show, using multimedia display is recognized with 91% accuracy, but the multimedia display is never seen by the model since it is static in the cabin. This shows that our model captures the motion pattern rather than the relationship between objects. In the ablation study, we find that the intermodal pre-training accelerates the training process and improves the generalization. Transfer learning experiments show that the model pre-trained with the simulated event dataset also improve the performance and can be fine-tuned with very little real event data. And finally, the temporal information in the sequence has a significant importance on the recognition. To conclude this representation, we propose an event-based architecture for driver distraction detection and action recognition. The proposed model achieves relatively high accuracy for the driver distraction detection on both simulated and real event dataset. We propose the event-based action recognition model performs on par with the state-of-the-art frame-based counterparts, showing effectiveness of the approach and the potential of the novel sensor. For future work, we can try fuse the multimodal vision information to improve the recognition performance, specifically for the objects that have texture. That's all for this presentation. Thank you for your attention.
Huijiao graduated from Hunan University, China in 2019, and he is currently working toward a PhD degree in computer science as a member of the informatics with the chair of robotics, artificial intelligence, and real-time system at Technical University of Munich, Germany. His research interests include computer vision, neuromorphic engineering, robotics, and deep learning.
Hello everyone, we are from Tongji University and Technical University of Munich. I'm Huijiao, PhD candidate at the chair of robotics, AI, and real-time systems lab. I will present our work on global local feature aggregation for event-based object detection on EventKITTI. Firstly, even camera is inspired with sensor that captures dynamic changes in the scene and filters out redundant information. Even the cameras has several advantages of no redundant background information, no motion blur, and high temporal resolution and high dynamic range. Which indicates even the camera has a promising future in the field of motion intelligence, especially for autonomous vehicles. For robust perception systems, it must show it must ensure the more accurate and robust performance in challenging environments. But for even the camera, it is still in its infancy. It meets two challenges, including lack of a large scale fine granular event-based dataset and lack of models targeted at the event sequence. To solve these problems, this work provides a simulated event-based automotive detection dataset named EventKITTI, and I effective event-based object detector. In event-based object detector, we use a transform module with closed loop age-based processing encoding to model global local dependencies among pixel-wise features. And we first introduce EventKITTI dataset. For EventKITTI dataset, it consists of object level dataset and video level dataset. Where we use VIG2E and eSIM to convert 2D object detection dataset, KITTI dataset, and multi-object tracking dataset to generate EventKITTI. And for event representation, we use temporal normalization to encode the event sequence as event frames. For our event-based detector, it consists of backbone and transformer encoders with age-based processing encoding module and multi-scale feature fusion module and detection head. In global feature aggregation, we use transformer encoder to capture long-range dependency from a global view, and we use age-based processing encoding in a single frame feature aggregation, and we use a closed loop learning module to in video frames feature aggregation. For global local feature aggregation, we fuse local features from the stage 2, 3, 4 of the backbone, and global features from the transformer encoder. Specifically, we use a multi-scale feature fusion module to aggregate global local features. We see in our experiments, we conduct three comparison experiments for EventKITTI. The results show that our EventKITTI can supplement a novel event modality information to the original KITTI dataset. And we further conduct experiments on the object level detection dataset. Obligation experiments show that the effectiveness of the proposed age-based processing encoding module and multi-scale feature fusion module, and compared with SOTA models, the proposed GFA-net achieves better performance in terms of speed accuracy trade-off in object detection on static frames. We further conduct experiments on the video level object detection dataset. The obligation experiments show that the effectiveness of the proposed closed loop learning, and compared with the SOTA video object detectors, the proposed GFA-net achieves better detection accuracy. We also display the detection results of the proposed models. The first column is ground truth. The second and the third columns are detection results of the proposed GFA net and CGFA net, respectively. In summary, our contribution are as follows. First, we provide a larger scale fine-grained event-based dataset, named EventKITTI. Second, we developed the event-based object detector. The proposed models, including GFNet and CGFNet, use the transformer model with closed loop age-based policy encoding to aggregate global local spatial temporal features. The proposed methods after performance certain models in terms of detecting accuracy.
So the third speaker is Huijiao Wang. So she is a doctoral student in the Signal Processing Laboratory of Wuhan University. Her research interests focus on event-based camera vision research, such as structured light, image reconstruction, 3D, and so on. So today, her talk is enhancing event-based structured light image with a single frame. Okay, yeah.
Thank you. Hello, everyone. I'm Huijiao Wang from Wuhan University. Today, I will present our work, enhancing event-based structured light imaging with a single frame. My presentation includes 4 parts. Structured light imaging is a classical 3D surface imaging technology for its strengths like simplicity and non-contact property. It's widely used in augmented reality and industrial testing. However, it's greatly affected by natural light due to the event camera's high temporal resolution and very high dynamic range. We consider to use event camera for fast, high-quality structured light imaging. However, real-world events often suffer from noise disturbances in spatial and temporal domain, which will lead to outliers, rough depth surface, and invalid phase, resulting in the failure of depth estimation. Considering above challenges, we built a novel prototype of structured light imaging based on event and frame camera. As shown in this figure, we built the EID's dataset, and we propose a multi-modal fusion network to get high speed and high resolution depth estimation. To elevate the systematic error caused by the misaligned event and frame data, we first apply camera calibrations and stereo alignment. As the figure shown, we introduce phase shifting algorithm with gray code to obtain reliable depths as the ground truth. The ground truth could help to quantitatively evaluate the result of the proposed MFFN. The multimodal fusion network consists of FFnet and an AppNet. As the resolution of the event camera and is often different from the frame camera, we firstly guarantee that the input of event phase and frame have the same resolution by downsampling with pixel shuffling. Then the multi-modal input are fed into FFnet for multi-level noise suppression and cross-modal feature fusion. Finally, the AppNet is employed to estimate a high-resolution depth surface for fused features. Due to the problems like the difficulty in fusing event phase and image intensity, noise, and the time delay in filtered event phase and the periodic property of the event phase, we designed the schema multi-level noise suppression and fusion. After extracting the shallow feature by SFE, FFnet uses the multi-layer noise suppression block to realize the fusion of different features in the DMHSA part. Since the low resolution event stream data edge being blurred and the detailed texture being lost, we reconstruct the high resolution by 3 solutions. First, the input image is collected in shuffle mode to retain the complete information. Second, the shallow features extracted by SFE module are used as the effective feature weights. Finally, in order to effectively utilize all features, 4 fully connected layers are used to complete the depth estimation. We choose RMSE and MRE respectively evaluate the accuracy and robustness of the module. This figure shows different models of accuracy, and this figure shows different models of our dataset. The column A, B, and C are white models, and the column D is colored models. Also, we collect 4 projecting periods to cover more types of data. In the following, we will introduce the experiments results to verify the performance of our proposed method. Here are quantitative comparison of our proposed MFFN to another state-of-the-art method, NFPP. We can find out the MFFN behaves best in both metrics from the table. Moreover, our proposed method is more robust for performance decreasing less when the model becomes more complex. Since the number of event data is more sufficient than the image, the depth value error obtained by NFPP event is much lower than that of NFPP frame. Here is quantitative analysis of performance comparison between our proposed MFN and NFPP. We can observe that there is a lot of noise in the NFPP event and frame because the traditional algorithm can't achieve absolute noise elimination. To verify the fusion effect of events and images, we set different fusion comparison event experiments. It's shown that FN and FP fail completely at high speed, while event makes a lot of errors due to excessive noise at 16 milliseconds. After event, as for event, due to the low resolution, it's difficult to obtain clear edge contour for depth estimation. From quantitative comparison in the table, we can observe that under different projection period, MFFN behave strongest robust, which is still valid under 16 milliseconds. In the same projection period, using the fusion net method of EF and MFFN has better results than using events or image alone. In order to verify the anti-noise performance of MFFN, we add noise experiments. It's shown that compared with using events alone, MFFN has better anti-noise performance against both spatial noise and time step disturbances. All in all, aiming at the event-based structural light imaging, our contributions are in 3 folds. We propose a novel hybrid EF-SLI system and a multi-modal feature fusion network. And meanwhile, we build the first EF-SLI paired dataset. In the future, structural light imaging in extreme environments can be achieved by pattern projection using the laser projector. And in order to save a lot of time in data building, unsupervised design for dataset can be carried out through the phase offset in the event phase. And thank you. Please feel free to ask questions.
Thank you.